So far, everything we've talked about has been certain. We have some choices for what to do, we have some outcomes. The outcomes are guaranteed. If you plant a strawberry patch, you're going to make $300 in profit. If you tell the workers to produce beer and champagne cases, they're going to produce 15 of them in 1 hour. This is not exactly how real life works. There might be a malfunction in the machines, and you might not be able to produce 15 cases in 1 hour. The strawberries might be a really good crop. They might produce $400 in profit, or they might be a really bad crop, and they might not produce any profit at all. So, to model these situations of uncertainty, we need a concept called a random variable. So, if you look at a regular variable, let's say you get your first problem with a variable might be solve for x, and you have some equation, you solve it, you get x equals 5. It's a regular variable. What this really is, normally you just find 5 on the number line and x equals 5. Or we could draw this bar on 5. We'll make this value 1. So this says x equals 5 with probability 1. For sure, x equals 5. Now we can extend this concept to a random variable. So this is a regular variable. Regular variable has a certain value, as opposed to an uncertain value. So a random variable might denote, like x equals 5 might denote, I don't know, the number of apples you buy from a store. A random variable might denote the roll of a die. We'll call this random variable y. So roll of a die could be 1, 2, 3, 4, 5, or 6, and before you roll it, you don't know what it's going to be. So it could be any of them, each of them with probability 1/6. And we can shade that in. This probability distribution represents the value of your random variable. You don't know what it is. It could be any of them with equal value. Note that the area of the shaded region is always 1. Here we have a 1 by 1 rectangle. It doesn't look like 1 by 1, but that's 1 by 1. This is a 6 by 1/6 rectangle. Okay, another random variable, we could have a roll of an unfair die. Also fine. Let's say I really like the value 3. I'm going to roll 3. Let's see how tall I want to make this. Scale doesn't really matter. I can redecide scale on every problem. I'm going to roll 3 with probability 1/2. And every other number with probability 1/10. There's my probability distribution. We'll call this variable z maybe. The area you can check is still 1. We've got 1/2 here, and then 1/10 times 5 there. So another half. Total area is 1. Okay, so those are random variables. In probability theory, you can do the same thing with random variables as you can do with normal variables. You can add them, multiply them, whatever you need to do. To decide what to do, we need the concept of independent and dependent events. So consecutive rolls of a die are independent events, meaning every time you roll it, it doesn't affect the next time you roll it. If I am about to roll the die, you don't say, wait, like, what were your last 10 rolls? Because I need to know that to know what this next roll is going to be. No, if it's a fair die, it's always going to have this probability distribution for the next roll. Dependent events might be like amount it rains each day. If you're about to fly to a new city and you want to know if it's going to rain tomorrow, you might want to know if it rained today or yesterday. And I looked this up in Seattle. Apparently in Seattle it only rains 156 days out of the year, out of 365-ish. We'll ignore leap years for now, which is about 43%. Okay, so if I have no information I say it's going to rain tomorrow with 43% probability. But if I know it rained for the last 10 days, we get grumpy when it rains for a bunch of consecutive days in a row because it's unlikely. We've had 10 days in a row of rain, but it doesn't happen that often. So if it rained for the last 10 days, well, if we don't look at the weather forecast at all, we might hope that it's not going to rain tomorrow. So one example in math that shows that these are different, for example, we want 10 consecutive rolls of 1. On a die. What is the probability of that? Well, each roll has a probability of 1/6. For independent events, we can multiply them. So 1/6 to the power of 10. Pretty small. Pretty unlikely to get 10 consecutive rolls of 1. What about 10 consecutive days of rain? It is not going to be, the probability is not going to be 156 over 365 to the power of 10. Weather is not that simple. Whether it rains tomorrow depends on whether it rained today. So those are dependent events.